In this video, we're going to introduce the definition and the concept of a piecewise defined function. And I'm going to show you some examples, and in order to solve these exercises, I'm going to have to use some techniques from things we're going to be learning later in the class, like how to find the equation of a line, and so on. So I just wanted to give that little caveat. For now, what I want you to try to understand from this lecture is just the definition of a piecewise defined function and the notation that goes along with that. And if you're not understanding some of the other things, that's okay, just follow along with me. And later in the course, when you learn how to find the equation of a line, for example, this will make a little bit more sense. So for now, let's just talk about what is a piecewise defined function. So it's a function that's defined in pieces. So far, we know a lot about reading graphs, and we've seen several different types of functions. So for example, I could have a function that looks like this, and if I was asked to find the domain and range, I would say, well, these arrows make it look like it's going to negative infinity on the left and maybe to positive infinity on the right. So the domain is all real numbers, and the range is all real numbers too. We've also seen some functions that had smaller domains, like maybe the domain was just the positive numbers, like the square root function, and the range was also the positive numbers and 0. We can take the square root of 0. So now what we want to do is we want to say, well, what if we broke up this domain into pieces? Like say maybe here and here. Let's say this is x equals -2 and this is x equals +3, just for example. And then what if instead of following this function all the way all over the domain for all real numbers, what if instead we changed at a certain point? And so maybe we have a closed dot here, but starting here, we do a straight line instead. And then I get all the way to x equals 3, and let's make this an open dot too. I get all the way to x equals 3, and then I do something else. Maybe I do a different straight line. So the first question you might ask is, well, is this a function? It looks a little strange. I'm not sure that it is a function. So we can go back to our definition of a function, and we know that a function is just a special type of relation where for each x in the domain, we have exactly one y in the range. And if I look at this picture here, that seems like that is satisfied. For each x in the domain, I do have exactly one y in the range. So this is a function, and this is what's called a piecewise defined function. I could also have, just to show you, for example, I could also have a gap here. So maybe I say from x equals 3 to x equals 5, I'm not doing anything. And then I start again at 5, and I go on some other function. That's totally fine as well. That's still a piecewise defined function. And the only difference between the two examples is that our domain won't be all real numbers anymore. We'll have this interval between 3 and 5 missing from our domain. Okay, so let's talk about, now we know what a piecewise function is, let's talk about the notation. So if I say that I'm giving this function a name, and this function is called f of x, this is the graph, how would I express this idea in algebraic form? Well, I would say f of x is equal to, and then I would start a bracket. And for as many pieces as I have, like here I have 3 pieces, I'm going to need that many rows. So I'm going to put these blanks here, and we're going to fill them in. But you wouldn't actually write these blanks typically. So how would I fill them in? Well, for each function, I would know the equation of the function. And since I just made up this function, I don't actually know the equation. So I'm just going to write equation of the curve. Originally it was some snake-looking thing, right? So the equation of this function, whatever that is what I would write here in the first blank. And the corresponding blank in the right column would tell me which part of the domain I'm following that function. And we talked about this looks like it goes all the way to negative infinity. So I would say it's from negative infinity to negative 2 now. I stopped at negative 2. So I would write x is less than or equal to negative 2. And I chose less than or equal to because of the closed dot. Okay, next I would write the equation of the blue line. And again, I just made up this picture, so I don't know exactly what that is. And then I would say in the corresponding blank, which part of the domain are we following the blue line? Well, that would be when negative 2 is less than x, and x is less than 3. And I chose strictly less than in both places instead of less than or equal to because I have open dots. What would my third piece be? My third piece would be equation of the green line. And in the corresponding blank, I would say which part of the domain we're following that equation, and that would be when 5 is less than x, or we can say x is greater than 5. Again, I'm choosing greater than instead of greater than or equal to because I drew an open dot. And this is absolutely a function, and this is how we would describe this function, except as I said, in practice you wouldn't put the black lines, the blanks. You would just write these equations. Okay, great. So another thing that I want to point out is that in real life situations, we're often going to need piecewise functions because in real life situations, things change over time. So we might be following one line for some time, then later we have to change and follow some other line. So this word problem is going to be an example of that idea. I want to tell you a problem-solving technique here before I start reading it, which is that anytime you're reading a word problem, try to circle or underline important information that you might need later. And you might not always use all of the information that you circle or underline, but sentence by sentence, try to understand what the problem is telling you and if that could be important for solving your problem later. If it is, just go ahead and circle it. So I'm going to do that while I read. First, it says, one of the longest stretches of straight and flat road in North America can be found on the Great Plains in the state of North Dakota on State Highway 46, which lies just south of the Interstate Highway I-94 and runs through the town of Gackle. A car leaves town at time t equals 0 and heads east on Highway 46. That seems important because I see that they've given me a variable and a number. So t equals 0 is important. And I'm also going to remember, what does t equals 0 means? T equals 0 means the time that we left town. So a car leaves town at t equals 0. I'm heading east on Highway 46. I'm not sure if that's important. Then it says the car's position in miles at time t in minutes is given by the graph of the function below. That also seems important, so I'm going to underline that our position is measured in miles at time t. Time t is measured in minutes, and that's given by the function below. It goes on to say that they've labeled some important points on the graph, and if it looks like a straight line, it is a straight line. Then the problem asks us to discuss, in everyday language, the behavior of the car over the provided time interval. So we want to look at the picture, and we want to try to understand what this picture represents. We can see that because I can divide the domain into pieces, and over different pieces of the domain, I'm following different functions. This is a piecewise defined function. Okay, very good. Now, what does this picture mean? Well, the first thing I notice is that it starts here at the origin, and there's nothing to the left of that point. I also see that the axes are labeled T and S. So the problem told me that T stands for time, it's measured in minutes, and it's how many minutes we've been driving away from the town. It also told me that the position is measured in miles, and it's how many miles away from the town we are after t minutes. So that suggests that this s, this dependent variable, should be position in miles. And what does it depend on? It depends on the independent variable, time, in minutes. So then it asks us to describe, in everyday language, what is going on here. So this point 0, 0, I can understand that that means that when 0 minutes have elapsed, we have traveled 0 miles. Well, that just means we didn't start driving yet. So no time has passed, we didn't start driving yet, so we didn't cover any distance. Then I see that there's this point, 57, 63.8. I know that the first entry in the ordered pair is time, so 57 minutes corresponds to 63.8 miles. So that tells me that in the first 57 minutes of my trip, I drove 63.8 miles. Then I see another point here, which is 68, 63.8. That tells me that at time 68 minutes, I've also driven 63.8 miles. Well, that's the same distance I had driven at 57 minutes, so that means I didn't move in that time between 57 and 68. But then it looks like I must have started moving again, because between 68 minutes and 104 minutes, I've gone from 63.8 miles to 106.8 miles. So let's try to write that up. So we'd say the driver drove for 57 minutes and traveled 63.8 miles. Before stopping for 11 minutes. Where did I get 11 minutes? Well, I just did 68 minus 57 because I knew that in that time frame I didn't travel anywhere. Okay, before stopping for 11 minutes. Then they kept driving for another, how long? Well, let me go back up and see. It was from 68 minutes to 104 minutes. I'll do 104 minus 68, that's 36 minutes. So they kept driving for another 36 minutes. And how many miles in that 36 minutes? Well, however many is the difference between 106.8 and 63.8, that should be 43 miles. Then they kept driving for another 36 minutes and another 43 miles. Then I noticed that at the point 104, 106.8, it looks like we have another flat piece. So I'm just going to say before stopping again, because it looks like they stopped again, and we're not sure why. That's fine. Okay, that would be plenty of information. You could also include that they were driving east on Highway 46 away from the town, but the important part is really that analysis of what's going on from the picture. Okay, the next example gives us the graph of a piecewise function and asks us to find its equation. So this is where I'm going to need to use finding the equation of a line, which we haven't talked about yet. So just follow me through this example and you'll get kind of a sneak peek of stuff you'll be doing in a couple of weeks. Okay, so I'm going to give these three pieces names. I'm going to call them L1, L2, and L3 for line 1, line 2, and line 3. And I'm going to go ahead and sort of set up my piecewise function notation because I know that I'm going to need f of x is equal to, and then I'm going to have 3 blanks and 3 blanks here for the different pieces of the domain. Now, like I said, we're not actually going to write those blanks, but I just want to make sure that I leave my bracket big enough that I have room to write 3 equations. Then I need to find the equation of each of these lines. Well, L1 is just a horizontal line, and I know that the horizontal line just has the equation y equals whatever the height is. So in this case, y equals -6. Instead of writing y equals, because the y equals is already basically taken care of by this thing, I'm just going to write -6. So that's the first line. And for which piece of the domain? Well, the arrow tells me that it goes to -infinity in terms of the x coordinates. And it keeps going up until x equals -5. So this is for x less than or equal to -5 because it's a closed dot. Okay, now I can see that my second line picks up at x equals -5, open dot, and it keeps going until x is equal to 2 with a closed dot. So I can also say -5 less than x less than 2. That's going to be the domain for the second part. And then the same thing with the third part. Let's go ahead and fill in the domain. It starts up at x equals 2 and it goes to infinity. So this is for x greater than 2. And since the closed dot was here with the second line, I need to make this one less than or equal to 2. And this one strictly greater than 2. Now let's find the equation for these lines. To find the equation of a line, I need 2 points on the line. So I'm going to say this point is 2, -2, and choose one other point that looks like it has nice coordinates maybe here. This is -2, 3. Here I have 5, 6, 7, -7, 7 and -7. And another point that looks like it maybe has nice coordinates is here, 10, 11, 12, and -5. Okay? I want to find the slope of L2. So I use these 2 points. And you may be familiar with the idea of rise over run. So rise over run means I'm going to take the difference in the y coordinates, that's -2, -3, and divide by the difference in the x coordinates. That's 2 minus -2, or 2 plus 2. So I get -5/4. And then I'm going to write the point slope equation because the point slope equation just requires me to have one point and the slope. I have more than enough information, and that point slope equation is going to be y minus one of the y coordinates. I can choose whichever point I want. So let's take 2, -2. So y minus -2 is actually y plus 2, and that's equal to the slope times x minus the x coordinate. Now since I chose this point, I need to use the x coordinate for the same point. So that's going to be x minus 2. Okay, so I'm almost done, but I need to get y by itself because my function already has y equals. So I want to get y equals something. So I'm going to say this is y equals -5/4x, distributing this -5/4x. Let's make this, so plus 10/4, which is plus 5/2. Then I need to subtract 2 from both sides. Subtract 2 from both sides. I'm going to subtract 4 over 2. I'm just making it a common denominator. So this is y equals minus 5 over 4x minus 1/2. So I can fill that in here and say this is minus 5 over 4x minus 1/2. That's the equation that corresponds to the part of the domain between -5 and 2. Okay, let's do the exact same thing for line 3. I need the slope of line 3. So that was my work for line 2. Slope of line 3, I take the difference in the y coordinates. So say minus 5 minus minus 7 is plus 7 over 12 minus 7. So this ends up being 2 over 5. And then the point slope equation, I can choose either point. I do y minus the y coordinate. Let's do y minus minus 5. So y plus 5 is equal to 2/5 times x minus the x coordinate. And since I chose the point that has the y coordinate minus 5, I need to take that corresponding x coordinate. So it's 12. So x minus 12. But I need y by itself. So I have to add 5, subtract 5 from both sides. So subtract 5 from both sides. And while I do that, I'm also going to distribute this guy. So that's going to give me y equals 2/5 x minus 24 over 5. And so let's get a common denominator here. And instead of subtracting 5, let's subtract 25 over 5. So that gives me y equals 2/5 x minus 49 over 5. All right. Perfect. So I'll write that in. 2/5 x minus 49 over 5 is the equation for the third piece, which corresponds to the section of the domain for x greater than 2. So this is exactly how you would describe a piecewise function in terms of the pieces and the chunks of the domain, and we found the equations for the line, which you'll know how to do soon. Okay, third example. A floor refinishing company charges $1.83 per square foot. Let's go ahead and underline that. To strip and refinish a tile floor for up to 1,000 square feet. That should be important. There's an additional charge of $250 for toxic waste disposal for any job which includes more than 150 square feet. So we want to find an equation for what they will charge to refinish a floor. It says when x is less than or equal to 150, when x is greater than 150, and then sketch the graph. So this becomes a piecewise function because we have these two different situations. What happens when x is less than or equal to 150? What happens when x is greater than 150? So let's start our function notation, and let's say I probably need a little more room here. Let's do it down here. Let's say f of x is equal to, and we know that one part of our domain is going to be when x is greater than 150. The other part is when x is less than or equal to 150. I'm going to add one more thing. I'm going to say 0 less than or equal to x. Because just like in the picture when we were driving, we're not going to have anything to the left of 0 because you can't have a tile floor with negative square footage. So we know that this is going to be how we're going to break up our domain from 0 to 150, from 150, and there was one more piece of information. It actually said up to 1,000 square feet. So let me fix this. This should be from 150 to 1,000 because it said here in the problem up to 1,000 square feet. So that was important. Okay, so this is how we break up the domain between 0 and 1,000. We cut it off at 150. And now we want to write the equation. Well, it told us that they charge $1.83 per square foot. We're doing x for square feet. So it's 183x when the square feet is less than or equal to 150. For jobs for square feet more than 150, we just add a $250 toxic waste disposal fee. So it's still $1.83 per foot. We add a $250 disposal fee, and there we have our piecewise defined function. Then the problem asks us to identify which picture should be the right one. So I know that my domain is from 0 to 1,000 and that I'm changing the rule of the function at 150 with 150 included here in the numbers that don't require the fee. So let's look at the pictures. We have different situations. I see that some of the pictures stop at 1,000 and some of the pictures don't, like this one doesn't. So we definitely want to stop at 1,000 because our domain stops at 1,000. I also see that some of the pictures include the closed dot with the lower line, and some of them includes the closed dot with the upper line. So which one should be right? Well, we said that 150 was included with the part where we don't pay that extra fee. So it looks like this should be right. So out of all of the choices, this is the one that has the correct domain and has closed dot and open dot in the right places. So this is going to be the correct piecewise defined function to describe this situation. Let's see another example. A restaurant offers a catering service which costs $21.50 per person with a $102.25 service charge. For parties of 40 or more, a group discount applies and the cost is $18.50 per person, along with the service charge dropping to $51. So we want to write a piecewise linear function which calculates the total cost t of the catering service which serves n people. So that's telling us they want us to write this t of n, and we have two situations, for parties of 40 or more or for parties of less than 40. And this reminds me that in the previous question, they actually told you to call the amount C for cost. So we want to actually be careful with these things. This letter C is just the name of the function. So in some sense, it doesn't matter. But if the problem told us that we should name our function C, then we want to be careful and make sure we name our function C. Okay, so same thing here. We're going to name our function t, and t is going to have independent variable n, where n is the number of people. So where does our domain get split up? Well, it seems like it has to do with the number 40. 40 or more. So 40 or more means greater than 40 or greater than or equal to 40. It should be greater than or equal to 40 because it's 40 or more. So 40 or greater than 40. And that tells us that this other part should be x less than 40. So if you have 40 people, you get the discounted rate. And again, I'm going to start this at 0 because we're not going to have a party with negative people in it. And I need to be careful because we're not using x here, we're using n. Okay, so this is how we split up the domain. If n is between 0 and 40, then we pay one price, whereas if n is greater than or equal to 40, we pay a different price. And what are the two different prices? Well, when n is less than 40, it's $21.50 per person. So I'm going to say 21.5 times n plus 102.25. And if n is greater than or equal to 40, meaning that I have 40 or more people in my party, then I only pay $18.50 per person, or 18.5 N, plus $51 fee. So these are going to be our two situations, and this is how we would write our piecewise defined function. Okay, another example, a contractor purchases gravel 1 cubic yard at a time. So this might be important, I'm not sure, 1 cubic yard at a time. Let's hang on to that. It says a gravel driveway L yards long, 6 yards wide, L yards long, 6 yards wide, is to be poured to a depth of 1 foot. Find a formula N of L for the number of cubic yards of gravel the contractor buys, assuming that he buys 8 more cubic yards than are needed to be sure that he'll have enough. Okay, that's kind of a lot of information, but let's think about our driveway. So here's someone's driveway, and the problem tells us we're going to have depth here as well. What is the depth? The depth is 1 foot. The width is 6 yards, and the length is L yards. Well, I can't have measurements in both feet and yards, so I want to either convert yards to feet or feet to yards. How do I know which way to go? The question asks us to find the formula where we put in L in yards. So I think our best bet is going to convert feet to yards. So 1 foot, well, we know that 3 feet is 1 yard. So if I only have 1 foot, that should be 1/3 yards. Okay. And this essentially becomes a formula for the volume of this rectangular solid. So the formula here of the volume of this rectangular solid would be 1/3 times 6 times L, which is 6/3 is 2L. Okay, so 2L is the volume of this thing, and the problem also told us that he's going to buy a little bit extra, no matter what the volume is. He's going to buy 8 more cubic yards to make sure that he'll have enough. So find a formula for the number of cubic yards that he needs to buy. I'm going to say our formula should be N of L is equal to 2L plus 8. That's fairly simple. Then it says, assuming that no driveway is less than 3 yards long or more than 9 yards long, find the domain and range of N of L. Enter your answers as comma-separated lists. So it tells us that the driveway is between 3 and 9 yards long. So that should be the minimum length is 3, the maximum length is 9. That tells us the domain. The domain is between 3 and 9. And we can include 3 and 9. So I'm going to say it's the closed interval from 3 to 9. But it also asks us to find the range. So one thing we want to think about here is that if the length of the driveway is getting longer, then we need more gravel to fill it up. So intuitively, the shortest driveway is going to require the least amount of gravel, and the longest driveway is going to require the most. So if I just figure out how much gravel I need for these two situations, 3 and 9, then I will find my range, because everything in between is going to require some amount of gravel in between. So let's find N of 3. N of 3 is equal to 2 times 3 plus 8, which is 6 plus 8, that's 14. And N of 9 is 2 times 9 plus 8, that's 18 plus 8, which is 26. So then my range is everything from 14 to 26. But there is one catch here, and that goes back to a contractor purchases gravel 1 cubic yard at a time. So when I write the range as an interval, I'm saying that I could have 14.5 cubic yards, or I could have 19 cubic yards, or anything 19.5, 19 1/3, 19 1/10. And that's not exactly right, because according to this, he's only going to purchase gravel 1 cubic yard at a time. So what do we need to do? We need to rethink this just a little bit. Our range should only be able to be the integers between 14 and 26. 14, 15, 16, all the way up to 24, 25, 26. And then that means our domain is going to change as well, because our domain then should only be able to be whichever numbers correspond to 14, 15, 16, to these integers. So how will I know? Well, it should be that because the function is 2L plus 8, every 1/2 of a cubic yard is going to add. So because L is multiplied by 2, for every 1/2 that I put in for L, 1/2 of a yard that I put in, then I go up by 1 in the range. So this should be 3, 3.5, 4, 4.5, ... up to, well, I need to stop at 9, so say 8, 8.5, and 9. Okay, so I know that's a little bit tricky, but the point here really is just that because the problem restricts us to this idea of only being able to buy 1 cubic yard at a time, which again is more like a real life situation, then we're only going to get these separated points of how much gravel he can buy. And that brings us to part C, which says, assuming that no driveway is less than 3 yards long or more than 9 yards long, sketch a graph of NL. Well, that's why you see we have a couple of options that are dotted lines versus solid lines. So the solid lines are representing everything in between 3 and 3 1/2, like 3 1/3, which we know isn't a choice for us. And the range, also, we only have these integer values. So it needs to be one of the dotted pictures. And how do I choose which one? Well, I'm going to choose the one that corresponds to the right domain. So assuming that this is 3 and this is 9, this looks like the right picture. When I compare it to the other option goes all the way down to 0, and that's not right for our situation. So we're going to say this is the closest resemblance to the picture that we would draw if we sketched this out. Okay. So the last question here in the lecture asks us to match the functions with their graphs. So here we see several examples of the piecewise notation, and we want to be able to match the corresponding picture. So I see that the first one, I'm going to number these 1, 2, 3, and 4, and then I'm going to give these graphs names A, B, C, and D, and we're going to just try to match them. So I can look at the pictures and I can see all of them involve lines, straight lines, but only graph A also involves a parabola. So then if I look back at my choices, I also noticed that only the first function involves x squared, so this must be my graph A. Now the other thing I want to notice is how the domain is broken up. We have x less than or equal to 2, and then the line starts at x greater than 2. So that means I'm going to get a closed dot here and an open dot here. And it also seems like these should go on because the domain isn't restricted. So it should go to negative infinity and positive infinity. Okay, so that was a little simple because that's the one that wasn't only straight lines. So now how are we going to figure out amongst these others? Well, I think our best clue is going to be looking at this domain and where it breaks up. Since it's different for each of the three options, we should be able to find that in our graph. So number 2 follows the line 2x plus 3 for all x less than negative 1, and then the line 3 minus x for x greater than or equal to negative 1. So which of these graphs changes its behavior at negative 1? It looks like C. So C must correspond to this. And then I also want to know which one gets the closed dot and which one gets the open dot. It looks like the line 3 minus x, that should be this guy, gets the closed dot, and this is the open dot. Okay? Now let's see if we can figure out between B and D which one is number 3. Number 3 is the constant function 3 for x less than 2, and then it's the line x minus 1 for x greater than or equal to 2. Well, B is the graph that changes its behavior at exactly 2. Again, I have the arrows because these domains go to positive and negative infinity. And I have an open dot here because it's strictly less than 2, closed dot here because it's greater than or equal to 2. That must mean that D goes with number 4, and let's take a look here. We have x when x is less than or equal to 0, closed dot and arrow, and we have x plus 1 when x is greater than 0, open dot and arrow. So that looks exactly right. Okay, that is the last exercise in this lecture note. So I'm going to stop the video here. And just as I said before, we want to just try to focus on understanding the notation, the piecewise notation, understanding why these are in fact functions, and how to make these choices about open dots and closed dots and breaking up the domain. For now, we don't have to focus too much on knowing the equations of the functions and how to find the equations of the line or the equations of the parabola, because those are skills we're going to build up in future lectures.